let's look at how to remove all the redundant computation. Yeah. We want to find an easy way to remove the redundancy. All right. Yeah. We want to use the recursion, but the only thing we need to improve is on this redundant calculation part. Yeah. So there is a very important idea in computer algorithms. Yeah. How to improve the algorithm? Method 1. Yeah. Yeah. Method 1, we do not use the recursive algorithm. We use iterative algorithm. We can avoid redundancy. Iterative algorithm. Okay? Let's just calculate the Fibonacci number by a for loop. In this way, you can see we do not need to do redundant calculation. Yeah. Each Fibonacci numbers, we only need to calculate it once. Yeah. Yeah. One by one, each time. Yeah. So the problem can be fixed. Okay, all right. So here you can see we have an easy fix, but there is one question in this simple algorithm. Although it is very simple, very fast. Yeah, so this algorithm is pretty fast. How fast it is? If we use the asymptotic notation, it is big O of n, this fast, linear. Yeah. People call it linear algorithm. Yeah. And the old one, very slow one, big O of theta to the nth, much slower. You can see the huge difference. Huge difference. Okay? Yeah. Yeah. All right. But this simple algorithm, although we can solve this problem, it's a nice solution, but there is a potential problem here. So what's that? Because you get around recursive algorithm. You get around it. Yeah. You get around it. Is it a good thing or bad thing here? You get around recursive algorithm. Is it a good thing or bad thing? Yeah. You have good part and a bad part. Okay? The good part, you use much less computing resource and it is very fast. The good part. The bad part also big. The bad part also very big. Now what's that? You lose the power of recursion. We know recursion is very powerful. Recursive algorithms are very powerful. You lose the power. All right? Yeah. So this is not a good method. Okay? Because you lose the power. Okay? So we want to keep the power of recursion. And we want to remove the redundant calculation, but we want to keep the power of recursion. That's important. So we don't want to throw away recursive algorithms. The huge power from the recursive algorithms. So our second method we want to do. Still use the recursion, but we need, at the same time, we need to remove the redundancy. All right. Yeah. So method number 2, this time, there is a very important idea. Simple but important idea to allow us to make it happen. Yeah, so this idea Extremely simple, but it's big. In computer algorithms, it is a big idea. All right, what's that? Let's see. Recursive algorithm without, yeah, that's our goal, right? So we don't want to eliminate recursive algorithm. We only want to eliminate redundant computation. We can make it happen by a special method to organize our data. Here, the key solution is on data organization. So we find a nice way to organize our data. Here you can see how important it is data organization. Okay? All right. Yeah. All right. Use an array. How to organize data? Here, I give you the explicit idea. Use an array to store calculated values. A short, simple sentence gives you the main point of the solution. You organize, here, let me explain this sentence. First, you need a data structure here. A simple array is good enough for the data structure to store temporary data, temporary results. To store calculated values. What's the calculated values? Fibonacci numbers, intermediate Fibonacci number, not the final. Our goal, we want to find the final Fibonacci number. But when we find the final Fibonacci number, we need to calculate a lot of intermediate Fibonacci numbers, right? But those intermediate Fibonacci numbers, you do not throw away, okay? You store all those intermediate Fibonacci numbers in an array, in a simple array. In that way, you can eliminate redundant calculation. That's simple. Okay? Yeah? So make sure that no value is calculated more than once. Each Fibonacci number, you want to make your algorithm guarantee that it is only calculated once. Not more than once. The second time when you need to calculate the same Fibonacci number, you do something different. You stop it. You stop the calculation. Do something different. If you can develop some mechanism to make that happen, that's a huge improvement. That's the huge improvement. All right. Yeah. So this idea is so important. So people call it dynamic programming idea. So it's a topic in our chapter 8. So here I want to give you a short, simple introduction on this dynamic programming. Let me spend some time to explain this general idea for this dynamic programming. In our project number 2, right, we will implement Fibonacci numbers in 2 different algorithms. The first one, brute force algorithm, and that one, you will have this big O of phi to the n, exponential slope algorithm. That's the first one. Second one, you implement the dynamic programming idea to make it how fast it is. Yeah. How fast, big O of n. Yeah. Same as that one, but this one we preserve the recursion. We do not throw away the huge power of recursion. We want to keep the power of recursion. But at the same time, we get a same efficiency, big O of n. Yeah, all right. Yeah, the idea is so simple here. But here, let me talk about the main idea of dynamic programming. So what's the dynamic program? Dynamic. Yeah. So your data is dynamic. Yeah. Think about when you calculate Fibonacci numbers, you generate your data dynamically, right? So you calculate Fibonacci of 2, 3, 4. The data comes in a dynamic way. Yeah. All right? Yeah. So you need to manage your data dynamically. So that's the dynamic part. Programming. What's that programming? Yeah. So this special word, yeah, because here we use the meaning of the programming in its old meaning, not current meaning. Current programming, yeah, so people know you're talking about computer programming, right? Coding, yeah, that thing. No. The old meaning of programming is not that. Yeah. The old meaning of programming, it's different. Yeah. Because at old time, no computers. So no programs. Okay? Yeah. So at that time, the programming meaning is, old meaning, it is tabular, the data. Okay? Yeah. So you organize the data in a table. Okay? In a table. You use a table to organize the data. That's the programming. Okay? You use a table to organize data. Okay? Yeah. Use tables to organize data. That's the meaning of programming. Okay? Yeah. All right. So here, we need to organize our data in an appropriate way. Okay? But this problem is very simple. So we use array to organize our data, not table. Yeah, because array is 1D, table 2D, right? Yeah, we know when we talk about table, it's 2D. So this array is a 1D data structure. Table is 2D data structure. Yeah. But 1D, 2D, not that important. Okay? Not that important. It is just some data structure to organize data. Okay? 1D, can we treat array as 1D table? It is. Yeah? Because it's a name problem, right? It's just a name. Okay? So we can treat 1D array as a special table. How about that? We don't need a 2D. We just need a 1D way to organize our data. Okay? Yeah. So 1D, 2D, 3D, any number of dimensions. Can we call them all tables? Yeah, it's okay. We can generalize the meaning of table. So any data structure, if we use to organize data, we can call it's a table, right? Yeah. So that's the special meaning of table here. Yeah. But there is another meaning for this method. Organize the data in this way. So that's people call it dictionary method. So this dynamic programming is also called a dictionary method. So why is that dictionary? This word is important. Okay? So dictionary gives you some more properties on the way we use our data structure. Yeah. Because this dictionary, dynamic dictionary, we can store the data in this dictionary, but there is another property we can see from this word dictionary. We can look up from the dictionary. We need to do the lookup operation. Look up another property. Yeah, so this word, you can see the lookup part of this special algorithm. We need to look up from the dictionary. Okay? Yeah. So people also call it a dictionary method. Then, what's the dictionary? These tables. Our array is a 1D dictionary. Tables, 2D dictionary. It could be 3D, multiple D dictionary. Okay? Yeah, that's a dictionary. So you store the temporary calculated data in your dictionary. You need to design the structure of your dictionary. Okay? Yeah. And later you need to use your dictionary. Yeah. For looking up the data you want to use in your calculation. Yeah. So that's the dictionary method. Yeah. So that's the dynamic programming. Okay? All right. Yeah. All right. So the idea, dynamic programming. Yeah. Yeah. So here, let's write the main properties of this dictionary method. First, store the data, the dynamic data, right? In an organized way. Step 2. Yeah. Look up the data when you need it. Yeah, that's the dictionary method. Dynamic programming. Yeah. Here we need to do that. We need to use this method to remove the redundancy. Okay? Yeah. Our dictionary just a simple array. Okay? When we calculate the Fibonacci numbers, after we find one Fibonacci number, we store it in our array dictionary. Okay? Next time, when we need to calculate a new Fibonacci number, before we do the calculation, we look it up in the dictionary first. If we can find it in the dictionary, don't do calculation, just to return the value from the dictionary. Yeah? You already have it in your dictionary. Why you need to recalculate it, right? Don't do the calculation, just to retrieve it. Okay? Because retrieve it is much faster than calculate it. Okay? Retrieve it, just to read the operation. Extremely fast. Okay? No calculation. Yeah. Okay? Yeah. But if you cannot find it in your dictionary, then you do the calculation the first time. So you only do, for each Fibonacci number, you only do the calculation once. Never more than once. Because after the first time calculation, you just do the lookup. Okay? The dictionary always returns the known values to your intermediate data. Yeah. That simple idea, so simple, right? Yeah, but this idea is so big, so important, so powerful. Okay? So it preserves the power of recursion. It saves the recursion. Otherwise, it's so slow. How can you use the recursion? If it is like this, exponentially slow, how people can use the recursion? People cannot. Okay? So this dynamic programming saves the recursion. People can still use the recursion, the power of recursion, but eliminate all the redundant calculation. All right. Yeah. So here. All right. Yeah. So now our method number 2. So based on that idea, we just do some simple modification. We can, solve the problem. Yeah. All right. So here, we already talked about that. All right. So the main points, the 3 main points here. Then we write the code. Also very simple, but we need to do some careful management on our dictionary. So this name, known capital F. Yeah. So the known value, okay? We will put the known value of the Fibonacci numbers in this array, known F. All right. Initially, this known F value array contains all 0 values. Yeah. All right. Then, the first step, before we do the calculation, we do the detection. If the current Fibonacci number, known f of I, if it is greater than 0. Greater than 0, that means it contains a calculated Fibonacci number. Because if not, then it should contain 0, right? Initial value is 0. If it's greater than 0, that means you already replace it by a known Fibonacci number. Okay? Yeah, that's the detection step. All right. Return the known value, that means no calculation, right? You stop the whole function and you return the value. So all the remaining calculation, stop it. Yeah. All right. So after this line, that means you need to do the first calculation, first round, first time calculation. Okay. So 2 base cases. Then this time, because it is the first time, so you do not avoid the first time recursion, right? So S equals recursive function call, 2 recursive function call. Okay. All right. Yeah. So after you get the value, you assign S to this your dictionary, known f of I. Update your dictionary data stored in your dictionary, and also you return it. Okay? Yeah. Yeah. So look at this dynamic programming idea. So simple. Yeah. Yeah. But it preserves the power of recursion, and it can also eliminate redundancy. Yeah. Yeah. So this idea is very important. Okay? Yeah. So after you learn this example, yeah. So later, when you solve problem by recursions, yeah, you need to think about if your recursion contains redundant calculation. Yeah. You need to think about, at least you need to investigate a little bit. If you find that your algorithm contains redundant calculation, then you need to consider, you need to use the dynamic programming way to avoid recursion, avoid redundant calculation. Yeah. All right, so that's the main point. Yeah. All right. So after this topic, next we need to study the Fibonacci number and the golden ratios, C.2. Closely related to the golden ratio concept. Why the Fibonacci numbers are closely related to the golden ratio? Since, very interesting. For the golden ratio, later I will talk about the definition, how to define the golden ratio, and why is this number. So, but here, the Fibonacci number they have a lot of good properties. For example, so this picture, this diagram, so people find some interesting properties. First, for the non-zero Fibonacci, because only the first Fibonacci number is 0. After that, all non-zero. So F1 is 1, F2 also is 1. So you use the Fibonacci number as the side of a square. Okay? Then you place those squares in a special way. The first two non-zero Fibonacci numbers, you put them together, so you get a rectangle. But the next one, F3, F of 3 Fibonacci number, the side is 2, side 2, you can, make alignment. So you can make the first 3 non-zero Fibonacci numbers align. This way you get a larger rectangle. Okay? Next Fibonacci number, side 3, you can, align them in this way. So you grow the size of rectangle. Every time you get a nice rectangle. Okay? Well aligned rectangle. Yeah. So that's the first property. But another one people also see, if you draw corner off, for each square you can draw corner off. So corner arc in some special way. For example, let's say first corner arc, second corner arc, third corner arc, next corner arc, right? See? Yeah. So you get a very smooth spiral curve like this. So another one, some people also observe some interesting property related to the well-known painting Mona Lisa. So the location of the eyes, some, things like that. So that's something related to golden ratio. So that, what is the golden ratio? How people get a special number? So this number is very special. Alright. So ancient Greek people, so they love math. So many people in their spare time they work on math, try to solve some interesting problems. Sometimes people argue, try to make some good story, try to define some interesting numbers with some interesting stories like that. Then they want to define some special number in the world, a very special number in the world. Okay? But that number should not be a plain simple number. Plain simple number, 1, 2, 3, so those too plain, not interesting. So they want to make that number very special. But you need to convince people why that number is interesting, right? Yeah. So those smart big stop. Try to convince people. So this number is very special. Here, that's their story. Okay? So they put two line segments together. The first one with the length A, the second line segment with length B. So they join them into a larger line segment. Okay? The length of this joined line segment, A plus B. Then they try to make this special number from these three numbers, A, B, and A plus B, three numbers. Try to make that story. Alright. They claim, so, we need a special number to have this property. What property? The ratio of
the shorter length of the shorter line segment A over the length of the longer line segment B. A over B ratio is some ratio, special ratio. Happens to be the ratio of another two line segments. Shorter one over bigger one. So the second ratio should be also from two numbers, numerator smaller, denominator larger, and the numerator, sorry, A is longer, sorry, A longer, B shorter. So then the numerator should be larger, and A plus B larger, right? Denominator smaller, we just use the length of the longer line. Okay, then you can find a ratio that satisfies this condition, and that ratio is very special. Okay? So that's the story made to define the special number. So let's try to find this special ratio. After we simplify the right-hand side, we get a 1 plus B over A. You can see B over A and A over B. These two ratios are special ratios. They are reciprocal to each other. These two ratios are reciprocal to each other. Okay? Yeah. So they are not independent. They are co-related. The relationship is the product of these two ratios equals 1. Okay? Alright. Then, to find the ratio, introduce a variable, one variable x for the first ratio, then the second b over a, that's 1 over x, reciprocal over x. Okay? Just the 1 over x. Now, you get a one variable equation. X equals 1 plus 1 over x. This simple equation. One equation for one variable, we can solve it. We can solve it. It's not too hard. So next, let's solve this equation. Let's find the solution of this equation. Solve quadratic equation x squared equals x plus 2. That is the quadratic formula. Okay? For the general quadratic equation, when the coefficient a, b, c, a not equal to 0, the x equals this quadratic formula. Okay? Now, let's apply this quadratic formula on this special quadratic equation, ABC. So we can find x equals 1, 2 cases, plus minus. 2 possible solutions. Plus minus root of 5, and the whole number over 2. After that, these two roots, are they both possible for the situation we have here? Because here our x means ratio of two line segments, right? Ratio of the length of two line segments. That must be a positive number, right? Yeah. Ratio of two positive numbers. So it is a positive ratio, but when you look at it, 1 minus the root of 5 is a negative number. So the second root is a negative number, so it cannot be the ratio of two lengths of two line segments. So we drop the negative root. After we go back to our original question, we can draw the negative root. So we only take x, that ratio, that special ratio, a over b should be 1 plus the root of 5 over 2. That's the in order to, so those people, in order to emphasize the importance of the special number, so they call it the golden ratio. The good thing is, this number is a lot of nice numbers. A lot. Yeah. Right. And in this number, because it's important, so people use a special Greek alphabet to represent the special number. Just like pi. Yeah? Pi is an important constant. Yeah? People use a Greek alphabet pi to represent that famous constant. Here, another one. So not as important as pi, because pi is used a lot. So this B golden ratio is also used as a special constant. All right, magic formula. Now, talk about some math formula for Fibonacci numbers. Here, there is some very special formula for Fibonacci numbers. Let me show you here. So what's that? F sub n Fibonacci. The nth Fibonacci number equals, look at this formula, so special. 1/√5 times parentheses. Inside parentheses, term, the first one, e to the n, golden ratio. What is golden ratio? The second term, minus numerator -1 to the n over e to the n. So this formula is closely related to the golden ratio. Now you can see why golden ratio is so special. Another special thing is, we know Fibonacci numbers are all integers, right? All integers. But the golden ratio is this special number. Golden ratio here, because there are infinitely many digits after that. So we call it irrational. Irrational numbers. Okay. The real numbers can be divided into two categories. Rational numbers and irrational numbers. So what are the rational numbers? What are the irrational numbers? So the rational numbers has a property. Every rational number can be represented as a ratio of two integers, okay? n over n. Every rational number can be represented as a ratio of two integers. That's rational. Irrational number cannot be represented as a ratio of two integers. So this 1 plus √5 over 2, it cannot be represented as ratio of any integers. So that's what people call irrational number. Okay? Fine. So here, E is an irrational number. You raise that irrational number to the nth power, then you minus some, another special irrational number. Then after that, you do division by √5. Suddenly, you get a nice integer, Fibonacci numbers. So that's the reason this formula is so special. Okay? So special. So you use an irrational number expression to represent integer. Okay? How to get that? So that's another story. How to derive this special formula. So that's another story. Now we will see that story later. Okay? So we will see that story later. All right. actually I complete power C. Yeah. So the power C, we introduced this Fibonacci numbers. We talk about Fibonacci numbers. But we have something left, our last part D. How can you connect the Fibonacci number to golden ratio? How to discover this one? The question is, for me, question. How to discover it? Okay? That's not easy, because nobody can guess this, right? No matter how small one person is, there's no chance that person guess the formula for Fibonacci. No way. Right? How to connect to the golden ratio? Nobody can see it. So you have to find some systematic way to solve it. Systematic way. Not just in this recurrence rotation. All the recurrence relations. How to solve. If you have that systematic way, you can solve it. This is your solution. Solution of this systematic way. All right. Yeah. So at this point, I finished power C. Yeah. So I have nothing to cover today. Yeah. So before you leave, let me ask you another time. What are those questions you want me to solve? You want to give me hints. This assignment. Do you have, this is your second